from Andhra University in the year 2009, Masters from SV University in the year 2003, Bachelors of Technology from SV University in the year 2000.
Yes, sir. Yes.
He is having more than 20 years professional experience. He served as assistant professor, associate professor at various levels in various prestigious colleges and also at NIT Warangal. His main areas of research are solid lubricants in machining processes, nano cutting fluids in machining, vibration assisted machining, modeling and simulation of manufacturing processes, composite materials, and AI and ML applications in machining processes. He handled several sponsored research projects, and among them, few are completed and few are ongoing. Most of the projects are from DS, ARCI, SCRB, CRG, and NIT Warangal, and few other from SRG, etc. Yeah. So he is having one patent to his credit. The title is Drill Tool Assembly. And he has guided 5 research scholars who are defended and 5 are ongoing. And he has published one book on production technology along with Dr. KL Narayana and SP Ramna Garu. Yeah, he is having several book chapters to his account, and he has edited several book chapters. And he is involved in lab establishment at NIT Warangal. And he has got Best Reviewer Award from Transaction of Indian Institute of Metals. And he is a member of several board of studies, editorial board, etc. And coming to publications, he has published more than 70 international journals. Among them, 38 are SCI and 35 are from Scopus related journals. And he has published several international conferences and national conferences. He has organized several workshops like international level and national level, and he has organized I think 3 international conferences, and he attended as a guest lecturer, visiting faculty and also guest faculty in various colleges, and he has shared his knowledge in various platforms, etc. So with this brief introduction, I would like to invite Professor Vamsi Krishna Garu to address the gathering and take over the session. Hearty welcome.
Yeah, thank you, Venkatesh.
సార్ ఒకసారి చేసి ఇంకా చెప్పాలని కెమెరా
విజిబుల్
అవునవును
నిన్న ఎంతమంది మేడం
అంతేలేండి. అవును, ఇక్కడ మేడం నేను ఇక్కడే ఉన్నాను సార్. నేను
ఓకే
9:30 అయింది సార్.
Good evening, Manada. So today my topic is application of AI and ML in machining process. So I think in the previous session, sir explained very deeply about the neural networks and other machine learning techniques, etc. But anyway, I'm just going to give a small introduction, which is required for machining process, and then I'll go into the case study or examples of this machining process. So I think you already know all these things, maybe from your previous experience or maybe from the previous sessions. So this artificial intelligence is a broader field, and it encompasses a range of technologies like machine learning, and also it refers to the creation of intelligent machines that can perform tasks that typically require human intelligence. That means if we see some situations like we are driving, some obstacle is there, suddenly we can apply a brake. That means our brain adds to that, right? So similarly, in so many activities, we can immediately react, and that is there is a reaction for every action from our side. Similarly here, in this artificial intelligence, actually this machine can learn, that is what is available, and also it develops some knowledge, and also it reacts or take decisions. So it's nothing but artificial intelligence. So then here machine learning refers to the process of training a computer. So it's part of artificial intelligence. It train a computer program to learn from data so that it can make predictions or take actions based on new data. That is, for example,
ఎందుకు ఉన్నట్టుండి ఫస్ట్ నాకు చెప్పను అదే మీకు అది మైక్ ఆన్ చేసి చెప్పను ఎందుకు ఉన్నట్టుండి యాక్చువల్లీ ఒకసారి కాల్ చేయడం అయ్యయ్యో లేదు మీరు చెప్పేట కూడా నేను నాకు చెప్పాడు నేను కూర్చున్నాను కూడా
yeah. For example, we know there is one small equation that is equal to y is equal to mx. So of course we know this is a linear equation, and where this y is directly dependent on the x. Whatever may be the value of m, if x value is changing, y value is changing. That means if you know the constant value m, and we can able to predict y value for different x1 values. That is, we can able to find out x1 y1 or x2 y2, etc. So it's nothing but we need not go for artificial intelligence or machine learning or whatever it may be. We know, suppose we have some data, maybe different data points like x1 and y1, maybe at a different cases 1, 2, 3, 4, 5, etc. So we have some values, So maybe if you feed this data, or you can develop a curve which is x and which is y, then maybe if this is the line and the slope of the line is nothing but m. So we can do curve fitting, and we can able to find out m value. Once we know this m value for this data, we can write the equation y is equal to mx. This is a simple thing, right? The same thing this artificial intelligence also doing, right? So we have all these data x1, x2, x1, y1, x2, y2, x3, y3, etc. The same thing happening here, but the thing is these are small points and only a linear simple relation. So we can able to find out with the help of this curve fitting, or some writing the some linear equation, or maybe by using some statistical method, etc. But if this data is having multiple variables like x1, x2, x3, x4, etc., and also this is not linear, this is non-linear, and also the degree of freedom is more, higher degrees of freedom, then it is difficult for us to find out these constant values, or to find out the relation between this x and y, or something x1, y1, x2, etc. So now to understand this one, we use this artificial intelligence or machine learning. And then we see the deep learning. This is also part of machine learning. So it is a subfield of machine learning that uses artificial neural networks with multiple layers to learn from data. I think you already come across this one. So these neural networks are modeled after a structure of human brain with layers of interconnected nodes and process information in the hierarchical manner. So this is a broad area, like we have artificial intelligence which is required nowadays. We are using maybe unmanned vehicles, or maybe missiles, etc., etc., without human operator. So all these are with the help of artificial intelligence. I think maybe Google also using artificial intelligence. So if you search, maybe you can use, many of you are using Flipkart and Amazon, right? So if you search some product maybe 2 times or 3 times, from next day onwards they will send message to you, this product is available, or some 10% discount, 15% discount, something like that. Or if you search make my trip, such something, you search flights for Hyderabad to something London, maybe, then immediately they will send a mail. So flights rates are decreased or something. to attract the advertisement. So how these people know you searched about this flight or you searched about this product, etc. That's nothing but artificial intelligence. So this Google or whatever is storing your data, maybe your IP address and the product what you searched and everything, and then this one is sending to the particular uh, this Flipkart or Amazon, etc. That is the business of Google. That means this is not collecting money from the customer, but collecting. This is known as B2B. So they are collecting money. They are charging money from this business. This one, where they are selling the information to them. So this is what the artificial intelligence is working. This is a simple example. So many things are there. I think all of you know now about the chat GPT, etc. So this is what artificial intelligence. Among that, the machine learning is there, where we use any of the computer program to train and then to use the same trained algorithm for our purpose. And in deep learning, mostly we use neural networks, not the other techniques. So this is about the overall introduction of artificial intelligence. So then, so these are the different methods normally we use in artificial intelligence. That is artificial neural networks, or maybe genetic algorithms, or maybe fuzzy logic, or support vector machines, or Markov models, or decision and regression trees, or adaptive neuropathy interface, inference systems, etc. Of course, these are just examples. There are so many new algorithms that nowadays people are using. And then I'll just give you a brief introduction. Maybe already you know, but this is required for my case study. That's what I want to give. So this ANN is a type of machine learning algorithm that is inspired by the structure and function of the human brain. So these ANNs are composed of interconnected processing nodes or neurons that work together to perform a specific task, such as data prediction or image processing or speech recognition or something else. So the development of ANN was the result of an attempt to replicate the working of a human being. So if you see here, so this is the input 1, and this is input 2, and this is the input 3. So for example, you take a machining operation, then we have a lathe machine, so we are doing a turning operation here. So maybe the tool is here. So we can give feed in this direction and depth of cut in this direction. So then the rotation of this one is nothing but n. So we can calculate v is equal to pi d n. So this is nothing but the linear cutting velocity, and this is the feed, and this is the depth of cut for a simple turning operation. So in many machining operations, if you take any of the machining operations, so the inputs are different. Okay, so simply the input may be cutting conditions like that speed, depth of cut. So if you are changing the speed, then the outputs may be changes. It may be a force, or it may be a cutting temperature, or it may be a tool wear, or it may be a surface roughness or something else, maybe stresses, etc. So these are the cutting conditions we give input to the in normal machining process. And then again, here other things is the tool material as well as tool geometry also. And then the other condition input is, of course, anyway, the workpiece material properties are going to influence. So if the workpiece changes, then everything is going to change. So here tool and geometry, and then the coolant. So these are the main things which are going to influence our machining process. So if you are increasing the speed, then the force may be increased, or temperature may be increased, or tool weight may be increased, or roughness may be decreased, something like that. So we have some linear relation or some non-linear relation between this cutting velocity and these output parameters, whereas by keeping all other parameters constant. For example, if you are keeping this velocity constant and then you are changing the speed, then also it changes. If you are increasing the speed, then all everything is going to increase because the load is more. Similarly, if you increase the depth of cut, then the cutting force, temperature, tool wear, surface roughness, everything is going to increase. But we cannot work at minimum values of feed and depth of cut. Why? Because if you decrease the feed and depth of cut, the productivity may be very less. Material removal rate is very less. Similarly, tool. So what type of cutting tool material you are using, whether you are using carbide tool or tungsten carbide tools or maybe HSS tool like that, they're also going to influence. Again, this depends on the hardness of the workpiece or strength of the workpiece. And then the coolant. If you are supplying a coolant, then what type of coolant you are supplying? Water-based cutting fluid, or neat oils, or MQL, or NO cutting fluid. Like that, there are so many options are there, and also the flow rate of the cutting fluid, and where we are supplying this cutting fluid, location of the cutting fluid, and the way of application of the cutting fluid. Everything is going to change these output parameters. So not only these output parameters, other parameters also there were energy and residual stresses and the crystallization or recrystallization. Like these other parameters also there, like chip formation. Okay, like these other important parameters also there, which are very important. But normally we take these parameters in a simple way, but other parameters also very important. So if you see this overall system, this machining process, there are so many input parameters, maybe 10 to 15, and output parameters also maybe 10. Just I'm saying the example. So if the each parameter is changing, this output parameter also changes. And if these parameters are simultaneously changing, or that means either increase or decrease something, these parameters also changes based on this. So this is very complicated thing. We don't understand. Maybe we understand only for one parameter, that is also by seeing the past results. So, but what to do? So then if you don't understand, randomly you select something, some parameters, and if you work on that one, then what will happen? The performance may be less. So we need to understand how this each parameter is influencing on the machining performance, and then based on that we have to either increase or decrease, or maybe we can go for optimum cutting conditions, where these optimum cutting conditions gives the better performance. So this is normally our objective in any of the machining process. So these machine learning techniques or neural networks will be helpful to estimate these optimum conditions and to get the better performance in the any of the machining process. It may not be lathe, or it may be drilling operation, it may be milling operation, or any finishing operation, whatever it may be. So this is what we need to understand. So then how this ANN works. So we have a input layer, already I told you. So whatever parameters you want to consider, or whatever parameters you want to change, maybe for example speed, depth of cut, and coolant, etc. Then thus many number of neurons we take in the input layer. That is, the ANN receives input from one or more sources, which is fed into the input layer. The input layer is composed of neurons that receives and processes the input data. So whatever number of parameters we want to change or we want to observe, then that many neurons we give in the input layer. And then we have hidden layers. That is, the input layer is connected to one or more hidden layers, which are composed of neurons that perform computations on the input data. That is what we thought. So y is equal to mx, or maybe y is equal to mx plus c, or maybe something y is equal to something c1 x1 plus c2 h2 plus etc. Like this, any of the relation may exist. We don't know. That's why we don't decide any relation. Just we give data to this hidden layer. So then this input layer is connected to one or more hidden layers, so which are composed of neurons. The number of hidden layers and the number of neurons in each layer can vary depending on the complexity of the circuit. So the number of hidden layers may be 1 or maybe 2 or maybe 3 or maybe 4, as well as the number of neurons in the hidden layer also varies. It may be 1, 2, 3, 4, etc. up to n. So between I mean, depends on the number of input neurons or input parameters, and depends on this output parameters, the complexity of the network is going to change. That is the number of hidden layers, as well as in each hidden layer how many neurons are required. That is what we need to decide. So, and also here we have one activation function. That is each neuron in the hidden layer applies an activation function to its input, so which determines the neuron's output. So that means this each neuron has its own activation function. It's nothing but maybe we can write f of y is equal to something like this. Maybe c1 x1 plus c2 x2 plus etc. Or maybe c1 x1 square plus c2 x square plus etc. Like this. So this relation is nothing but this activation function, and this may be sometimes linear or non-linear. Normally we take non-linear because it also taken care of the linear relation. And then the output layer. The hidden layers are connected to the output layer, which produces the final output of the network. And the output layer is composed of neurons that apply an activation function to their inputs, producing the final output of the network. So here, if you want only one output, then we take only one neuron. This may be just y. Or if you want two outputs, then we take two neurons. If you want three outputs, then we take three neurons. Like this, here, these input layer neurons are changing, output neurons are changing, and number of hidden layers are changing, as well as the number of neurons in each hidden layer is changing, and the activation function is changing. And then the training. So during the training process, the weights of the connections between neurons in the network are adjusted. This is what the weight function. So this means, like for example, I can write y is equal to maybe 2x1 plus 3x2 plus 4x3. So if you know x1 comma x2 comma x3 values, if you substitute into this, then we can get 5 values. So here this is nothing but the weight of this x1, 3 is weight of this x2, etc. This is a simple relation, okay? But if you take a complex relation, non-linear or higher degree non-linear function between the input and output, then this weight is going to vary. Of course, we start with some value, but once the training is going on and we test the input data is giving, and this neural networks is going to train, and we are getting some output data, but this output data is not matching with our experimental output data, then we go back and change these weights. So we adjust the weights till the output data of this neural network as well as the experimental values are matching. Then the network is ready. Then we can use the same network to the other data. So that is what training. So during the training process, the weights of the connections between neurons in the network are adjusted to minimize the difference between the predicted output and the actual output. Actual output means it's nothing but experimental value, and predicted output means it's nothing but a the output what we are getting from the neural network. So then the testing the network has been trained. So once the network is trained, we have to test. That is nothing but it can be used to make predictions on the new data. So the input data is fed into the neural network and the output of the network is compared to. So that means suppose we have 100 data points, then we take normally 80 data points for training and 20 data points for checking. Okay. So with these 80 data points, if you train this network and weights are adjusted to get the output, then we remove this data and we use this data only. So for this data also, the output is same as the actual value, actual output and predicted output are same. That is, the error is minimum. Then our weights or number of hidden layers or number of neurons are correct. And whatever the activation function what we taken is also correct. Then we use this network for any other data of the similar kind. Okay, not for everything. That means, for example, what I explained to you. So we are working on AISI 1040 steel. This is the workpiece material, and we took one lathe machine. Suppose some 5 kilowatt conventional lathe machine. So for this workpiece material, this machine tool, whatever the input parameters we are taken, that is feed, depth of cut, or tool material, or coolant, etc. And here the outputs may be force and temperature. So for this data, we train this network. Then this network is efficient only for this data. Suppose you are changing this workpiece and you are taking titanium alloy, then it may not be same. Why? Because if the hardness of the workpiece is changing, the strength of the workpiece is changing, and also the brittleness, all these things are changing, then the relation between these parameters and these output parameters is different. So this network is suitable for the similar type of workpiece material on the same machine and within the range of these input parameters. Then we can able to predict the output parameters. Like that, there are some constraints for this one. So then, what is the benefit of this artificial neural network is there is a flexibility. That is, these are highly flexible and can be used to solve a wide variety of problems. So we are discussing about machining data. So not only machining data, if you have any data like casting process, welding process, or forming process, or some other heat treatment process, etc. For any data, we can able to predict the output parameters if you have a data of some experimental data, and for a particular input data we can able to predict the output data, and then we can able to recognize the image, or we can able to uh, identify the speech, or maybe natural language processing, etc. Or maybe we can control the autonomous systems like uh, um, I mean driverless vehicles, etc., etc. Also, so this is one of the benefit, and also the other one is adaptability. So NNs can learn from experience and adapt in new situations, making them well suited for tasks that require continuous learning and adaptation. So continuously it can adapt the experience and maybe changes its weights and activation function. Then it can able to work on other data also. So then the parallel processing. So it can process parallelly large amount of data, and it will give fast and accurate results, and also robustness. So this can handle noisy and incomplete data, making them useful for real world applications. So maybe if you have one image and in that image is not clear, maybe we can remove the noise and we can apply some filters, etc. And image processing technique. That again, that can be given as input to the ANN. Like this, we can use some incomplete data also in the ANNs, and non-linearity. So this can model non-linear relations between inputs and output. That's already we discussed. allowing them to learn complex patterns and relationships in the data. That is what I told you. Maybe there are more number of input parameters and more number of output parameters, and there is a complex relation between these parameters. Then also it will work. And fault tolerances. So that is nothing but ANN can continue to operate even if some of the neurons or connections in the network fail or damage. That means maybe in some data, all the neurons are having some weights, but in another data, one neuron is inefficient or not required to act. Then also these neural networks is good to predict the outputs. Then another technique what we use in the machine learning is this fuzzy logic. That is, this fuzzy logic is a method of reasoning that resembles human reasoning. That is, this approach is similar to how humans perform decision making, and it involves all intermediate possibilities between yes and no. So that is the conventional logic block that a computer understands, takes precise input and produces a definite output as true or false. So normally if you have some computer or program something, maybe if you use if else statement, so it will give only yes or no or true or false. But so this is like this. So it uses the Boolean logic. If it is 1, it will yes. If it is 0, it is no. Mostly this may be used in the ANN, but if it comes to the fuzzy logic, okay, the question is it cold? Then it will not, based on the temperature, suppose the temperature is 10 degrees centigrade. So then it will say maybe very much cold or little cold or very less cold, etc. So then this works. This is example. Maybe you can give range. Suppose the temperature is minus 20 to minus 10 degrees centigrade. Then too cold or minus 10 to 0 degrees centigrade, one range, and 0 to 10 degrees another range, and 10 to 17 degrees. Like this, you can classify whatever you want. You classify. So here we use the 3, but maybe you can use 4 or 5 or something. So only thing is you should build a logic based on the given conditions. Then it will take or it will give your output. So this architecture works like this. So we have a fuzzifier. So this is the fuzzifier. That means the fuzzifier is responsible for converting crisp input into fuzzy sets with degrees of membership. That means it takes input values and maps them to fuzzy sets using the membership function. That's like this. It takes this input data and it matches with these functions, and it belongs to 1 or 2 or 3. So for example, if the input is temperature, the fuzzifier would map the temperature value to a fuzzy set such as cold, warm, or hot with corresponding degrees of membership. Similarly, we use in a machining also. For example, you are giving the temperature, maybe output is a force, for example. So if the force is less than 200 newtons, then we give one fuzzy classifier. Maybe this is 1. And if it is 200 to 400 newtons, then it may be 2. Then 400 to 600 newtons, then it may be 3. Or 600 to 800 newtons, then it may be 4. Like this, once the data output is monitored like this, then it immediately classifies the output force is either in the class 1 or class 2 or class 3 or class 4. Again, this class 1 may be something, class 2 may be something like that. So this leads to maybe tool wear or surface roughness or something like that. Then we can do or we can see this one with the help of some output data. And next one is inference engine. So this is the inference engine. It's nothing but the intelligence one. So here already these rules we are giving as a input. So the inference engine uses fuzzy rules. This is what fuzzy rules we use. to make decisions based on the fuzzy input. So if the decision here maybe if the cutting force is greater than 800, then stop machining. Or if the cutting force is between 400 to 600, then use coolant. If the cutting force is 200 to 400 newtons, maybe reduce cutting speed. And if it is less than 200, maybe you can continue. Like this, you give some rules, and this intelligence or inference engine checks the cutting force value, and it operates either it stops the machine or sends coolant, or maybe reduce the cutting velocity, or maybe it continue in the same condition. Like this, this inference engine is used to take a decision here. And defuzzifier. So here again, this is nothing but the crisp data is already processed and it is changed or classified to match with these rules. Again, the output data should be the defuzzifier. So the defuzzifier converts the fuzzy output sets into crisp values. So it takes the fuzzy sets with degrees of membership and converts them into a single crisp value. So that is if you have stop function is something, then it uses function. That function, coolant function is something. So here the function is displayed maybe F4 or F3 or F2 or F1, etc. Maybe this F4 is stop function, F3 is coolant on, and F2 is reduced velocity, and F1 is continue in the same condition. So like this, and then we have a rules. So these rules contains all if then conditions offered by the experts to control the decision making system. So like this, we use this fuzzy logic architecture again in the machining process to take a decision, or maybe to change the input parameters, or maybe to stop the machining and do anything. Like this, we can use this fuzzy logic or fuzzy architecture. So these are two examples where we have the artificial intelligence in the machine. So normally we use this artificial intelligence in machining for so many applications. That is, first one is predictive maintenance. So that means we monitor machine tool performance and predict when the maintenance is required to prevent machine downtime, or maybe if the tool life, tool wear is more, then we reduce the tool wear, or maybe we improve the tool life, etc. So that is nothing but the predictive maintenance. And then tool wear monitoring. It also monitor tool wear in real time and adjust the cutting parameters accordingly to prevent tool failure and reduce the machining costs. So then we have these quality controls. That is obviously if the tool wear is high, then the surface quality is less, cutting forces are more, and the power consumption is more, and the accuracy is also less because the tolerances are out of the range. And this is nothing but a quality improvement with the help of the AI or ML. And then the material characterization. So based on the output parameters or that one also, we can able to predict the material parameters. That is, for example, one particular material. So the output is residual stresses. Okay. So if you have some data like for so many input parameters for a particular material, this is the input data, maybe speed, depth of cut, tool length, or tool geometry, etc., etc. So then the material is processed by some machining, that is turning process. Then the output is of course so many cutting force temperatures. But what we are interested in the residual stresses. But the thing is, this residual stresses is going to influence on the product lifetime. So this product life is not exactly output of the machining process. But if you measure these residual stresses And if you're able to develop some relation between these two particular products, then we can assess what is the lifetime of this product. So like this, by changing these residual stresses with the help of changing the input parameters, we can improve the efficiency of the process, and we can enhance the precision, that is like dimensional accuracy, and the feature geometrical accuracy, etc., dimensional accuracy and geometrical accuracy both. And then again, not only this one, maybe we can go for optimization of the process, that is to reduce the cutting force or to reduce the temperature or maybe to improve the surface quality, etc. What is the range of parameters or at what conditions we need to operate this one, etc. So we do all these things, predictive maintenance or quality control or efficiency improvement of the process or improving the precision of the manufactured part or process optimization with the help of these AI and ML techniques. So this is the main applications or different applications of this AI and ML in a machining process. So then we will see each one by one. So for example, we want to predict a cutting force using the artificial intelligence. So what we have to do, the same, whatever I explained already. So the input parameters is feed, cutting speed, depth of cut, coolant conditions, and vibrations. Vibration of the machine tool, or this is ultrasonic vibrations, is especially in the vibration assisted machining. Okay, so of course I am not going into the details of what is this process. So these are the input. So collect data from machining operations, including spindle speed, feed rate, depth of cut, and tool geometry, as well as whatever available. And then the process the data, that is clean the data, remove outliers, and normalize the data to ensure consistency. Because maybe we have 100 points, but among that 5 points are very abnormal, then we remove these 5 points, we take only 95 points. So then the feature selection, select the relevant features from the collected data that are mostly likely to affect the cutting force. So what are the parameters influencing this cutting force? We need to finalize. For example, in some process, suppose depth of cut is not that much important or not influencing much, then we remove this one like that. So then data splitting. This is what already I told you. The overall data, whatever available, we split the data into 70 to 80% as one set and 20 to 30% as other set. Then these 70 to 80% data we use for the training of the networks, and this 20 to 30% data we use for the testing of this network. So determine the architecture of the ANN, including the number of layers, the number of nodes in each layer, and the activation function used. So once we decide this input layer and output layer, okay, so we have to decide the number of hidden layers as well as the number of neurons in each layer. In each layer. So once we decide these two things, then the network is ready so that we can go for the prediction of the cutting force. So then the training the NN. So the train the NN using the training data, and the training process involves adjusting the weights and biases of the nodes in the network to minimize the difference between the predicted and this actual outputs. This is what already we discussed. Then validate. So we test the data with the trained model, and then we validate with the 20% data, and then model refinement. So refine the NN as necessary based on the validation results to improve its accuracy. So if the error is more, then we go back and improve by changing the number of hidden layers or number of neurons or momentum of the network or learning rate, etc. So here we should understand the word momentum. this is normally between 0 to 1. And also the learning rate, this is also normally between 0 to 1. So if this one is too high, also not good, too low is also not good. So normally we use 0.6 or 0.7 or 0.75, etc. And here also the learning rate we use in the range of 0.5. Why? Because if it is the learning rate is too high, then the network is not adjusted, weights are not adjusted properly. Or if the learning rate is too less, then the time taken is more, and maybe unnecessary data is also considered, etc. So this is why these two values we need to adjust and then go for the next one. And then the model refinement is nothing but that one, and testing. So we have to test the data, right? And then deployment. So once the network we are getting, then we have to deploy this network for estimating the similar type of data in the same process. This is the general steps involved in this ANN. This is for
Sir, I'm having a small doubt in momentum and learning rate, sir. Hello, sir.
yeah, tell me.
Sir, in learning rate, that it will changes that weight, no, sir. Slowly it will changes that weight value. By giving smaller value, I think it will changes the weight value. So what that momentum it will do, sir?
See, momentum also changes how the data is given or learned by this network. So, for example, I'll give you one paper which is having 10 lines, and I ask you to read in 1 minute.
Okay, sir.
So, how you can read that? That is different. I mean, the fast or whatever the pronunciation is different. Suppose if I give 10 lines, you can take 5 minutes, then it is different,
Yes, sir.
right?
Yes, sir.
So that is what the difference between this.
Okay, sir. Okay.
So then we can do tool condition monitoring also. So this is nothing but, if you see, we have a machine tool, right? So this is a machine tool, and we keep the dynamometer, maybe strain gauge dynamometer. So this is the workpiece, okay, and this is the cutting tool. So here, with the help of dynamometer, the strain gauge dynamometer, we are taking the cutting forces. So this is a dynamometer unit where we are getting the signals, okay. So these these cutting force signals are sending to data acquisition system, where we have computer and software inbuilt, etc. So what we can do is, initially, so online we cannot monitor the toolware. I mean, we cannot measure the toolware. So initially we conduct an experiment, and time to time, maybe for instant 1, 2, 3, 4, etc. What is the force and what is the toolware? What is the force and what is the toolware? What is the force and what is the toolware? Of course, there are certain input conditions. That conditions also different. So for each condition we are defining the input parameters, as well as the output is the force. It may be cutting force, speed force, or thrust force, etc. This is what actually the direct output. But these are direct output. This is online. That means we can able to take this data while the process is going on, while machining process is going on. But this data is offline. That means after the process is over, then only we can able to measure this toolware by using any of the tool makers microscope or other microscopes. That what we can do is, at different conditions, we measure the toolware after 1 minute, or after 2 minutes, after 3 minutes, after 5 minutes, etc. Then we can get all this data, and this data is given as input to the neural network, and where we can use this MATLAB and develop a function. So now this is the one we develop. This is the network or machine learning algorithm we develop. Now, once this is developed, then we incorporate this algorithm into the system. Maybe in the next time, when you are doing this cutting process, already this speed, feed, depth of cut, other parameters are there in the input machine, what we are already given, or maybe computer is observing from the CNC program. And then here there is a function which is developed that one, and then here we have other one where this from this dynamometer the cutting force are going and as input to the system. So these are also going. So now we know this, and this one we are monitoring. So already here there is a model based on this cutting force and these cutting parameters. What will be the tool wear? This model already we developed based on the previous data. So in the present experiment also, if you give all these parameters and the tool wear is, cutting force is varying here, by using this machine learning algorithm, we can able to estimate a tool wear. So once the tool wear is reaching maximum value, or maybe it is reaching the value where the tool failure may take place or roughness is going to increase immediately, we can stop the process, or maybe we can change the input parameters, or whatever decision we want, we will take it, or that also we inbuilt in the program. Maybe nowadays this adjustment of the input parameters also can be done by this algorithm from the CNC machine tool. So this is what the tool were condition monitoring. The previous one and this one difference is, in the previous case, the cutting force is directly we can able to see, but here tool where you can able to you cannot see when the process is going on, because this area is maybe covered by chips or covered by cutting fluid, etc. So this model will be helpful to monitor the tool wear by using the data of cutting forces for a particular input parameters. So in this way, this one is useful for estimating the tool condition. Okay. So is it audible?
Yes, sir.
Right. So this is what tool condition monitoring. So in this one also we have two different types of methods are there. That is direct methods and indirect methods. So maybe in the direct methods we can use either electrical resistance or image processing technique or tool geometry, vision system, etc. So we can able to measure these direct methods. In the indirect methods, that is what we use the temperature of the process or cutting force of the process to predict this tool wear. So this indirect method is decided or which can be used by with the help of so many sensors or signals, and we can able to monitor this tool wear by using this any of the machine learning algorithms. So this is actually the components of tool condition monitoring. So we have a machining process, and the inputs are given, and we have a sensors with accelerometers or microphone or dynamometers, etc. And we have a data acquisition system. All these are shown in the previous figure. And here we have a signal processing. That is, the data will be amplified, filtered, or normalized, or denoising can take place. Then from that data, feature extraction will be taken care. That is in the time domain frequency. And then if any abnormalities are there, why these abnormalities are coming, whether plank wear is more, or crater wear is more, or any edge crack is there, etc., etc. Based on that, the model will be developed and we can take a decision making whether we need to reduce the process parameters, or maybe we need to change the tool, or the decision can be taken. That is whether it is because of the wear, sorry, whether it is because of the wear or breakage or chipping, that can be decision can be taken, and based on that one, either you can stop the machine, or you can reduce the cutting speed, or maybe you can increase the cutting fluid rate, etc., etc. So these are the components of tool condition monitoring. So this is also another process where this is a machining process is going on. So this is maybe hand milling process. So that we use different types of sensors and here connected, and these sensors from these sensors we get different types of data. Maybe the data from the data we can reduce the noise, normalize, etc. And we can use any of the method, machine learning algorithm, maybe deep neural network, etc. And this is data is
Hello, sir.
already, yes.
So, what is training data and validation data?
Pardon?
What is training data and validation difference?
Your voice is not clear.
So, what is the difference between training data and validation data?
Training data and
Validation data in
validation
data
data.
splitting.
Yeah, that's what I told you. If we have 10 points, 8 points we use, and these 8 points is given as input to the network, so that based on this one, we decide how many hidden layers are required or how many neurons are required, what weight functions, all these things we decide based on this 8 data. Then we take remaining 2 data points, and the 2 data points again we give as input and we check the output with the network. And for the same data points, we have already experimental data also. This is ANN data. So if these two are matching, the error is minimum, then this network is good. Because the next time when you are using some data, we don't have experimental data. So directly we give inputs and we find out the outputs. So where we can check whether it is right or wrong. So that's why we have to validate it. Is it okay?
Yes, sir.
Right. So here also same thing. Maybe we use all these things. So offline we measure toolware, etc. And that input is given to the system or algorithm. And similarly, the data is also given online. So by using the previous knowledge and the present data, it gives toolware labeling. That is whether tool is failed or where is more, that is blank where or not where or data where, or maybe chipping is there on the cutting edges or edge is broken, etc. So then we take a decision and do this one. So this is also same. Just I am showing the other this one. So all these are same. The steps are similar to the previous one, where what we use for the cutting force prediction. Here also tool condition monitoring also we do. The steps are same. Maybe here we use the indirect method, which is the data is used in the image form or whatever it may be, that can be assessed or incorporated into the machine learning algorithm, and based on that it will take a decision. So for example, this toolware picture is there, then this can be analyzed by using image processing, and it will be decided. Maybe we have a flank where, or we have a crater where, or maybe we have notch where, etc. So these things again linked to this data. So if the signal is like this from the accelerometer, then there may be a flank wear. If the signal is like this, there may be a crater wear. If the signal is in this range, there may be a notch. Like that, from the previous data, we train the algorithm so that in the next time when we are using this algorithm for any other process, it can assess and it will give you the result, or it will give you the some indication. Then similarly, we can use the same thing for surface roughness also. So that is surface roughness, because the surface roughness is very important in the machining process. Like we need to get a high quality product with greater accuracy, so that not good, we cannot get. Many of the industries, they don't know at what point or at what parameters we get better finish. Only based on the operator experience or maybe trial and error they will get. So once they are getting good quality, they will continue with that one. But any other things is changing, that is workpiece material conditions, etc., then they don't know how to adjust these parameters. So that is normally in the conventional industries. So there also these machine learning algorithms are useful to predict the surface roughness. But especially in this machine surface roughness prediction, these linear regression models or decision tree models or random forest models are more useful. So I'm not going to discuss now what is decision tree, what is random forest, etc. These are all the different algorithms in the machine learning. Maybe we can use any of these algorithm to do or to predict the surface roughness. If you are anyone interested, maybe you can learn or you can study about the individual algorithms, right? So this is a general working methodology for any of the AI technique or machine learning technique. So normally we collect data from the experiment, and this data will be processed and given as input to the algorithm. Then here we develop a model, right? So this data will be given as uh, input to the model, so we can train here, and then we evaluate the model here, and from the final model we try to see what is the error, and based on the error what we are getting, then we go back and adjust this algorithm, whatever maybe the model we are using, maybe random forest or decision tree or artificial neural network or maybe deep neural network, etc., etc., whatever it may be. We go back, we do iterations, number of iterations, and for each iteration these weights will be adjusted, or maybe number of things will be adjusted, and finally we get the model. So that model will be used for prediction or for maybe optimization or for any other purpose, that depends on the developer model. So this is again some example, maybe in end milling process we do milling. So here we get the data, that data will be sent here. So maybe we have deep neural network, we have input, hidden layer or output, and then we have this LSTM. LSTM is nothing but a long short-term memory. That is each time this network uses a long and short-term memory. That's nothing but sometimes it uses memory from the previous data, or maybe sometimes it takes data from the present data point. So both it will use. By combining these two, we develop a network. So like this, we develop different types of networks, and then uh, we can get the final model. So this is CNN means convolutional neural network, DNN means deep neural networks. So here if you see, here in this one, the data will go from one layer to next layer, next layer, next layer. So once it is processed, then it will go to next layer. But whereas in the deep neural network, it's not like that. This each node is connected to all the other nodes of the next layer, and this is also connected like this. So here both parallel and series type of combination is there, but here it's not like that. It is only series type of combination is there. So this is what we use in the different cases. So then this is just from the one of the studies. If you use different models like linear regression model or decision tree model or random forest model or neural network, etc., for a particular data set, and this is the roughness value what we got from the data sample. So different things are there. So maybe comparison of the surface roughness what we are getting from different models. Of course, if we compare the true value, so this is the true value. So by comparing with this one, which is more nearer, suppose if we have numerical values, maybe we can find out the error, and then we select which model is working better for this particular data, right? So this is what the overall concept of artificial neural network or any other machine learning algorithm we can use in the machining process to predict either cutting force or tool wear or surface roughness or maybe anything, material removal rate or maybe residual stresses, etc., etc. But once the output parameter is changing, maybe the input parameters also change and network structure also changes, depends on the complexity, all these things. Okay, so this is what the overall thing we see or we need to understand in the machining process. So I'll give you one case study, right? So just 1 second. Right. So for example, this is one case study where we use ANN in prediction of tool wear and surface roughness. So I'll tell you here why we took this function. So where small t is the machining time and this S is nothing but the solid lubricant particle size. F is the cutting force, that means resultant force, and capital T is the cutting tool temperature, and K is the thermal conductivity of the lubricant. So initially, we took this function, that is tool wear is a function of all these parameters, and here also surface roughness is a function of all these parameters. So normally what we discussed previously, for any process, actually we have speed, depth of cut are the inputs. But here, to avoid more parameters, the cutting force is taken as, because cutting force already we are getting from the dynamometer directly through the experiment. So we took cutting force and to eliminate all these parameters. Okay, and also the extra things is here, uh, actually in this process we applied a solid lubricant. Okay, so here the parameters which are going to influence in the solid lubricant is these are applied in the form of powders. So particle size is important, as well as based on the type of solid lubricant, its thermal conductivity is important, because the thermal conductivity of this any of the lubricant coolant is going to influence the cutting temperature. That's why these two parameters are included in this model. Okay, and cutting tool temperature and cutting force are included in this one. Why? Because these are we can these two parameters we can able to measure online with the help of maybe thermocouple and with the help of the dynamometer. That's why, to avoid more number of parameters in the model, these two are taken, which can taken care of all these other parameters as input. But because, and also, sorry, these parameters are kept constant. That's why these two are sufficient. But we changed the solid lubricant particle size and also the type of solid lubricant. That's why these two parameters are included in the model. So now we assumed the tool wear is a function of this, that is machining time, solid lubricant particle size, cutting force, and cutting tool temperature and thermal conductivity. So then if you want to remove this one, this is assumed as a nonlinear equation like this. So then similarly this is also same, we assume nonlinear equation. Then this is given as input to the neural network model. And then here the first thing is the number of hidden layers uh, and number of hidden layer neurons are optimized. That is, this is the error we got when we took one hidden layer and increasing the number of neurons in each hidden layer. And this is the error we got when we are increased or we taken two hidden layers and number of neurons in each hidden layer is 3, 4, 5, etc. And when we take 3 hidden layers, sorry, this is 3 and this is 2 hidden layers, the error is like this. So once this is 1 hidden layer, this is 2 hidden layers and this is 3 hidden layers. That means from 1 to 2 error is decreased, again from 2 to 3 error is increased. That means even if I take 4 also, again there may be increase. So we are decided the number of hidden layers for this one is 2. So we optimize the number of hidden layers as well as then the number of neurons also. This is the one, and the number of iterations also. So how many iterations we have to do? So once we take 5,000 iterations, this is the error, and then we increasing iterations, error is going to decrease. Once we reach it to 20,000, later the error is not decreased much, maybe slight decrease. So there, either from here to here, this may be here, not that much degree. So this is maybe better, or if you want more accuracy, this is better. You need not go beyond that because the iterations are increasing. The time taken for this one is going to increase. So which is not acceptable. So we have to optimize this number of iterations also by seeing the error. Then based on this, like this, the inputs are the same 5, and we fix the hidden layers and number of hidden layers, and as well as the number of neurons in hidden layer, then the output layer. Here, so here for one network, toolware is output parameter, and for other network, this is other parameter. Of course, here we are showing in single diagram, but these are two different outputs, so two different networks are there because the weights, all these things are going to change. So then this is the tool plan. So that is what the relation between input parameters and output parameters. So this is the function which develops like a nonlinear equation, right? So here this is actually the predicted and experimental values for the tool for the boric acid solid lubricant in SAE40 oil, and this is the tool plank ware. Of course, we use a regression model also, but I did not include here. So if you see, this is a neural network value and this is the experimental value. This is experimental value, neural network value. When we use the 5% boric acid in SAE40 oil, and we use 20% boric acid in SAE40 oil. So that is comparison of predicted and experimental tool plant values while using this boric acid suspension in SAE40 oil. So then similarly, this is the error predicted. So this is for 5% and this is for 20%. So percentage error. So it is mostly maximum is 10%. So maybe if you increase or more try, the error maybe slightly reduces. So this is the predicted percentage error. Similarly, the same is used by changing the solid lubricant graphite with the same percentage 5% and 20% on the same base oil. Then again this is prediction of tool wear like experimental value and neural network value. Experimental value and neural network value. So then the error is like this. So this is the error for 5% and this is the error for 10%. Maybe it seems to be varied, but actually if you see the scale, these are below 10% only. Okay. So then this is the solid lubricant mixed in the base oil. Okay. So again, if we use solid lubricant in a dry powder form, so then again we can change the particle size, and previously we changed percentage of solid lubricant as well as type of solid lubricant. So same, at different cases, we developed experimental and neural network. So we predicted tool plan square. Okay. So that is, there are different cases and same procedure we follow. And this is also to flank where using graphite powder and this is same 50 micrometer size and 1 millimeter. Then again, boric acid in SAE40 oil for prediction of surface roughness. So here, if you see, we developed a number of models, number of networks to predict each parameter in each case. So these are all the different things. So finally, here what we predicted is tool where there are two cases. Number one is uh, solid lubricant plus SAE oil. So in this one, what is the parameter where it percentage of a solid lubricant and as well as type of solid lubricant, that is either boric acid or graphite, and percentage of solid lubricant. And the second case is solid lubricant powder. So here we again the parameters are particle size as well as same boric acid and graphite. So there are two parameters, right? So in the toolware itself, there are two different conditions. Lubricant condition, that is solid lubricant either in the powder form or solid lubricant in SAE40 oil. And again in each case there are two varying parameters. So for all these four conditions, like this is the one with boric acid, this is the one with graphite, this is the one with boric acid, this is the one for graphite. So there are four models are developed. And similarly for surface roughness, the same. First condition is solid lubricant plus oil. Same thing here, percentage of solid lubricant and type of solid lubricant graphite. And whereas in the second case also we used only solid lubricant, so in the powder form. So here the change is particle size and this one. So here also we have four models. Of course, maybe another four iteration models also there. Just I kept only NN models. Like this, for a particular workpiece, okay, and for a particular feed and depth of cut condition, and also particular tool material and tool geometry. So these are the things I kept constant. What I want to understand is, I want to understand the effect of lubrication in the performance of machining process. So where cutting force and temperature I can able to measure directly when the process is going on with the help of dynamometer and the thermocouple. Whereas these toolware and surface roughness I cannot measure. That's why these models are developed, and these are used to predict the tool wear and surface roughness online, so that when it is varying or it is beyond limits, then immediately we'll go back and check what is required to change, whether I can change the lubrication condition or percentage or lubricant, etc. Because based on the previous data, we can optimize this, and with optimum conditions range also we can keep. So we optimize for minimum cutting force or cutting temperature and tool wear and surface roughness, or we can decide this one. So these output optimized conditions we maintain. So if this tool wear is going beyond that, then we go back and change the input conditions of this lubrication. And if surface roughness is more, then again we change the input condition of this lubrication. So this is what different. I mean, this is one just one case study. maybe you can use this one for any different types of lubrication conditions, or by changing the workpiece, or by changing the tool, or by changing the cutting conditions, or by changing the total process instead of turning. Maybe you can go for milling, etc., etc. So this is what. Yes. So I think this is almost the last slide, or one or two more slides are there. So then maybe this we can apply to maintenance of the machine tools also. So from the machine tool also we can get this data, sensors data, different types of sensors we can use. That is, we may get what is the temperature rise in the machine tool in different parts, or maybe what is the noise level, or what is the vibration, etc., etc. So then this is recently we can call it as digital twin model. So we can check what is the things. So we use degradation mechanism, or material characteristics, or operating conditions, etc. So we take different types of data, and this data is continuously going to this machine learning algorithm, and here this algorithm can do analysis, and then send data to this I mean, this data will send to this algorithm. And similarly, from the machine tool also, the data is this is the observed data. So now this may be a present data, and this is the past data we have, and this one they can check the hybrid approach algorithm. Then we can predict exactly or accurately what is the status of the machine, when we have to go for maintenance, or when we have to stop machining, or what is the drawbacks, either tool is damaged, or maybe lubricant is over, or maybe some bearing is damaged, or something like that you can identify, and maybe you can go for the maintenance of the system. So this is also another one. Maybe nowadays we can check the energy output of this one, and from that energy also, by using image processing technique, we can predict how the process is going on. So this is a data acquisition system. We get data from the machine, and we use the database where we process all this data, and this is the data like this. So most of the data is here, but some of the points are outside. So this is anomaly detection using the LOF. LOF means local outlier factor. That is, these data points are outside the region. So this can be purified and then sent to whatever neural network or deep neural network, etc., developed, and then this sent to the model, and again we have a CNC control system. This data will be sent, and here we predict the energy consumption, or whatever this one, and then based on that one we take a decision what parameters need to change, because the energy consumption is going to increase, which is not good for our process, right? So like this, this is also one of the example for energy consumption. So the summary of this all these methods is, so normally this artificial neural networks gives good performance for complex behaviors, but limitation is long computational times and many parameters to be optimized. So whereas it uses mainly for the industrial task, or considered for normally an artificial intelligence standard. And we use genetic algorithm also, and this is very flexible. And here also the limitation is computational, long computational times, and sensitivity to parameters, but it optimizes the tasks. So we have the flexibility of optimization also. And then it use uh, fuzzy logic. This is a comprehensible models, and dealing with uncertainty most of the cases, and where we can use for complex problems, or many complex rules can be necessary. and usually less accurate than the more complex models. And here the main use is knowledge base or expert system. Or similarly, we have a support vector machine. This is also one of the machine learning technique where the good performance with complex behaviors and high dimensionality and depending on the kernel. Whereas the parameters tuning is required and long training time for big data sets depends on the kernel, as well as high dimensional data sets are required. Like this, just I tabulated few things. Based on this, similar to this, there are so many techniques. We have uh, advantages and limitations with each technique, and these techniques are useful mainly at certain conditions. So we need to understand, we need to apply these things. So this is what about applying these AI or ML techniques for the machining applications. So maybe this is, I just took small direct case studies. Maybe complicated things also we can deal. Maybe if we know Python and we can able to write a code for difficult things also. That all depends on the programming language. That's all from my side. If you have any doubts, please ask me.
Yes, sir.
Yes.
So basically, hidden layers we can consider to be weights.
Pardon?
The hidden layers can be considered as a weights, different weights.
No. Weight is different. Weight is associated with each
రీసెర్చ్
neuron.
స్కాలర్ అనుకుంటా సార్ అతను.
But hidden layer is nothing but one step of processing.
Okay.
Yeah, that's a function, not complete algorithm. That's a function. Yeah, right. Right. Yeah, definitely we will take polynomial function only. Non-linear polynomial functions only we will take, because we don't know. This data is not linear data. If linear data, we need not go for this much complicated machine learning, all this. Yeah, yes. Right. We take normally non-linear polynomial function.
Thank you, Professor Vamsi.
Thank you, sir.
Thank you. Any clarifications? Dear participants, any doubts or clarifications? Otherwise, we will conclude the session. Thank you.
Maybe I will send to Vikram sir or any of the coordinators. They will share with you, right?
Thank you, Professor Vamsi Krishna. Today we have one session.
Sir, if it is possible to send to mail, sir, PPT. Send to
Pardon?
mail. PPT, sir, PPT.
Yeah, that's what I'm saying. I don't have all mail IDs. So you are getting program schedule, invitation, link, everything from one mail, right?
Yes, sir.
So you can get this also from that mail.
Okay, thank you, sir.
Thank you, Professor Vamsi Krishna, sir, for giving elaborate discussion on the neural network and fuzzy logic, the application of neural network and fuzzy logic in the machining applications. And today we have completed two sessions. The first session by Professor Soundu Kumara sir regarding the application of AML in the advanced manufacturing process. In the second session, Professor Vamsi Krishna discussed about the importance of the AML techniques as a manufacturing system, machining system. So today we'll conclude the today's session. Tomorrow we have another two sessions. One session by Dr. Venkatesh sir, extending the previous session regarding the finishing process by using ALML technique. The second section on the multi-objective operation by Dr. D. Srinivas from IIT Madras. So thank you all. Thank you all for attending this session today.
Thank you so much.
Good night,
Thank
Vamsi
you.
Krishna.
Yeah, thank you, sir. Good night.
క్లాస్